Thank you very much. It is my great pleasure to be able to speak about WMAP 5 just after release, like a week ago was a release. I already gave 2 talks at the Perimeter Institute about different aspects of WMAP 5-year results. But today I'm going to update you on the what's new in WMAP, essentially quickly walk you through essentially everything that's written in this cosmology paper that I wrote. So obviously I have too many slides, so let's begin. This is the WMAP 5-year science team. What's on the left shown is the PIs, Chuck Bennett, and 6 co-PIs here. What's not shown is Dave Wilkinson, who unfortunately passed away just before the first data release. So these people initiated the WMAP. Then there were other people joined soon after they initiated the WMAP. Then these people, including myself, joined the WMAP after the launch. So, and we added to help the analysis. And WMAP has this system that young people just come, do the excellent job, and leave, and get job, and continue to do well. So this is entering graduation system. And these are the WMAP graduates, including Olivier up there. WMAP 5-year results are not independent at all on the third year or first year results, which means these people have spent enough amounts of time doing very good job in developing the analysis software and pipelines and all that kind of stuff. So we really we should congratulate the WMAP 5 together, all of us. Okay. So there was a press release. By the way, is this too dark? Is it okay? Is it usual thing? The brightness, is it okay? Okay. Okay, yeah. All right, no, as long as you're used to it, that's okay. Yeah. As long as you can see this, that's okay. Yeah, so we just had a press release on March 7th, last week. There are 3 items in a press release, so let me just quickly walk you through that. Evidence for the cosmic neutrino background from the WMAP data alone. Okay. The second thing is the instantaneous reionization at z equals 6 is ruled out. The third thing is the tightest constraint on inflation models to date. So let me just talk about those first. So before I get into that, let me just update you on what's new in the analysis. Okay. So this is the 5-year WMAP data. Galaxy is taken away, so-called internal linear combination map, ILC map. And visually, nothing has changed. Okay. And you still see this, some people catch this, SH, Stephen Hawking, it's still there. It's been there since first year release, it's still there. But we have to always remember that we have this galaxy to deal with. Before subtracting galaxies, we have K band, which is 23 gigahertz, Ka band, 33 gigahertz, Q band, 41 gigahertz, V band, 61 gigahertz, and W band, 94 gigahertz. Okay? What you see here is a synchrotron radiation, combination with synchrotron, a dust emission, and free emission that you have to take into account. The first thing we do is to just mask a certain region of the sky that has a very, very large galactic contamination. But not only that, we also subtract the galaxy. In fact, I think I missed one slide here. Okay? So we published 7 papers. First one is data processing climax and basic results, Hinshaw et al. Then Hiro et al. Is the beam, characterization of the beam. That's where we made a huge major progress in the 5-year analysis. Gold et al. Describes how we remove galaxy from the data. So not only we mask it, but also we reduce the foreground emission by cleaning. So this paper describes that. Then we also have to remove the point sources from the data. That's not something we want in the data. So we get rid of those. That's described in Wright et al. Then maps will be converted into angular power spectrum. So this paper, note title, describes how we measure power spectra and what the results are. Then these power spectra are fed into Markov chain Monte Carlo exploration of the parameters, cosmological parameters, and Dunkley et al. Describes how we do it and what our results are from the WMAP data analysis alone. So this gives you some numbers. Then in this paper, we describe how to make sense of these numbers and what happens when we co-add WMAP data with other data sets. like distance measurements from other data sources. Okay. All right, so we get rid of the foreground, and also we have polarization. This is again K, Ka, QV, W band polarization data. And you can't really see it very clearly from the back, but you see, so this, what's bright here is a large polarization intensity. But you see also directions here. You can't see it very clearly from back. You see the directions, so we also have polarization direction information here. And you see these maps are still contaminated by the foreground, but we remove them by masking and also removing what we think is the correct foreground template. And those analyses haven't changed much from the 3-year. We just have better data, so we have better idea about how to subtract the foreground. So these things haven't changed since the 3-year data analysis. But what changed is the beam. We now have a much better understanding of the beam profile. So what happens is the following. When we measure the power spectrum, right, the power spectrum, as you measure it from the data, has a beam smearing effect, right? Because you have finite width of the beam. If you want to extract the information from small scale, you have to take into account the fact that you have already filtered the data by your beam. That needs to be corrected. So the precise knowledge of the beam is required to do this job. Usually we don't have, of course, perfect knowledge of the beam. So what we do is to take our best guess of the beam, then put some error bar onto that. As long as your estimates are correct, estimates of error are correct, you're okay. Now we managed to reduce that error in the beam by a factor of 2 in most of the bands, and sometimes factor of 4 in some of the bands, some of the highest frequency bands, W band. That's a very significant improvement, and I'll tell you a little bit more about that. Calibration. So the way WMAP works is that the WMAP measures intensity from the sky, but you then have to convert that into CMB temperature, thermodynamic temperature. So you measure some intensity, you have to multiply some factor and convert that into temperature, say microkelvin, right? So that requires gain calibration. And we have also made some progress in doing gain calibration more accurately, and calibration error is now down from 0.5%, which is already small, to something 0.2%. So our calibration is very, very accurate now. Then lastly, there are a few other improvements, but these 3 are most significant improvements. Lastly, we're now using more polarization data. So for the 3-year data analysis, we used only 2 frequencies, Q band 40 gigahertz and V band 60 gigahertz, and we didn't use other frequency bands. The reason for that is that, for example, Ka band, that's 30 gigahertz. We didn't use it because we didn't think that we have understood foreground contamination in that band very accurately. So we didn't use that. But this time, I think we understood the foreground contamination there, so we're adding to it. So not only we have more years of data, but also we have better understanding of data so that we can use more data that we have, okay? More of the data that we have. So that's a progress. Now let me just talk a little bit about a beam. So what's shown here, there are so many plots, but what's shown in red is the beam uncertainty from the 3-year data analysis. What's shown here is the delta B over B, which means you are seeing the difference between 3-year beam and the 5-year beam. Okay? And because you can't see it, the numbers, let me just show you some numbers here. So this is L equals 100, L equals 200. This is about the first peak region of the CL power spectrum, then onward. So 200, 300, 400, and 2, 3, 4, and 5. Okay, here. And this is so what's showing in red is the error, 1 sigma error, and what's showing in black is a 3-year beam minus 5-year beam. If it is high, that means 5-year beam is lower. If it is low, then 5-year beam is if it is high, 5-year beam is low. If it's low, 5-year beam is high. Okay. Now, one immediate thing that you should take out from this plot is that the change in the beam is all within 1 sigma error. Okay, most of the cases, right, within 1 sigma error. This thing exceeds 1 sigma, but still, it's pretty good. You know? So change in the beam is fully consistent with the beam error that we came up with for the 3-year data analysis. And now, for the temperature analysis, we mostly use V band and W band. And that's here. So VV, W, 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 W. And if you look at it, this black curve is consistently higher, which means 5-year beam is consistently lower by about 1%. So this is 1%. Okay, this is 1%, 1%, 1%. Okay. So what that means is that you have to make a correction, a little bit more correction, to get the power spectrum. And now this is beam, and power spectrum is beam squared. So if it's 1% here, it's 2% in the power spectrum. So what that means is that you are now dividing power spectrum, raw power spectrum, by a smaller number, smaller by about 2.5%, to get the beam corrected power spectrum. So the resulting power spectrum is almost uniformly raised by about 2.5%. Yes?
And so did that end up all getting absorbed into the sigma 8, or did it fall on any other parameters?
It's not so obviously affect. So this change actually doesn't have an immediate consequence for the cosmological parameters, it turns out. This shape is not quite correlated with NS or sigma 8. But of course they are affected. But the two are much lesser degree than one might expect from this change.
Well, normalization, right?
Normalization has changed as well. Yeah, that's right. But that has an influence on sigma 8. But it's not the full story. Yeah. But thanks for asking that. It's completely non-Gaussian. It's completely non-Gaussian. It's totally wrong to use the Gaussian. And that's something we knew already from the past year. Yeah.
What factor does it suppress the power before you correct for it?
What's the...
At L of 200, what factor is it suppressing the power by?
Oh, what is the beam smearing factor before we make correction? I don't have the number off the top of my head. Yeah. But it's not factor 2. It's much less than that. Yeah. Okay. Now, but one thing I want to say is that but this 2.5% raise in the power spectrum is fully consistent with 1 sigma error of the 3-year beam uncertainty. So if you do the proper statistical analysis, then results are consistent statistically. Yes? This is a better understanding of the beam. So let me just get down to it. Okay, so what was the change? Okay. How do we measure beam anyway? So we measure beam of the Jupiter, right? So as we scan across the sky, we can integrate down the noise for the measurement of the Jupiter. So you're getting down, so you're measuring more of the outer skirt of the Jupiter by integrating down. So we have a much improved signal to noise ratio for the measurement of the beam. That's one thing, right? That will give you improved beam estimate. The other thing we have done is that you always hit this noise floor. Can we do better than that? And in fact, we can do better than that because we have a good idea about why beams take on the shape that we measure. That's all coming from mirror shape, distortion on the mirror, right? So we can actually do better than just measuring the spherical averaged beam. We can reconstruct the beam distortion and mirror distortion using the physical optics modeling. We essentially fit the Jupiter beam pattern by modeling by changing the mirror distortion. So we have this mirror. No, it's the physical. You are essentially trying to model the geometry of the mirror. So you have this spherically symmetric uniform mirror to begin with. You perturb it by adding some Bessel functions, right? Or spherical harmonics. And then you perturb the mirror until it actually matches the beam shape that you measure of the Jupiter. This will give you the physical idea about what the distortion is.
Mathematics is the same as adaptive optics. It's based also on the perturbation of the sphere.
Oh, that's a perturbation on the atmosphere, right? That's the atmosphere. Yeah. We are modeling the mirror. Okay. So that will actually give you a better idea about what the beams really are. You are mechanically modeling beam. So that has that's a very time-consuming process. And we just managed to do that for both A side mirror and 2 side mirror. WMAP has 2 mirrors. We managed to do that for both of the mirrors for the first time. That finally gave us the reduction in error by a factor of 2 to 4. Does that answer your question? Yeah. Yes?
Is the changes to the lens, is this something that could have been measured in the lab prior to launch?
Sure. Yes, so we did have some idea about the beam distortions. That's correct. But they will change in flight. And temperature environment is not the same, right? So we had to do it essentially in flight. Yeah. Also, we have this measurement of the far side robe. So this measurement can give you some idea about the beam in the sort of confined region in the main beam. Far side robe has been measured pre-flight and also in flight of the moon. So we measure the far side robe using a moon. But we have the measurement of the far side robe of the main beam, but the intermediate step is missing. So we use this physical optics modeling to fill in the gap. So we have a much better idea about the beam toward the very far side robe. So this is a huge improvement. But results are nicely consistent with the previous results within 1 sigma. So that was very good to see. And this is the 5-year CL. And so we have a nice measurement here. And now we didn't have much control on the third peak region before, but now we have better idea about what the third peak looks like. Yeah? So that's a good improvement. And now we are cosmic invariance limited to L of 530 here. Okay.
What is the situation with the low multiples?
Nothing has changed. Nothing has changed.
Do you have excess of evil?
We haven't looked, but I bet there is still, yeah. And this is the combination of WMAP and other measurements that go much beyond the WMAP resolution. So Akbar, Boomer, and CBI, they beautifully measured these higher harmonics. But let's focus on the third big region. And WMAP measurements, which is black, and other measurements in the color are consistent in the third big region. So we have a consistent picture in the third big region. That's very nice to see. Now, adding polarization, Ka band. Okay, how do we justify that? So this is now not the temperature, but EE polarization power spectrum in a very low L region. So you have L equals 2, L equals 3, 4, 5, 6, 7. Very, very low L, right? And what's shown here is actually the error bar that includes cosmic variance. Okay? So this is a true error, including instrumental noise and cosmic variance. And at this low multiple, the likelihood function of the CL is very non-Gaussian. So you're not allowed to multiply this by a factor of 2 to get 2 sigma error. Okay? This is 68% confidence level, but you are not allowed to do the factor of 2 multiplication to get 2 sigma. Likelihood distribution is very skewed. Now, having said that, so these are the sum maps. So you have Ka plus Q plus V divided by 2 to get this sum map, sum power spectrum. Then you have some signal. And this is something like 5 sigma detection of E mode power spectrum. But what if we just take the difference? Right? And because Ka has much more synchrotron, Ka minus Qb will be completely dominated by synchrotron if there's any residual foreground that we haven't accounted for. But we don't see any. I mean, it's completely consistent with zero signal. These blacks are only upper limits. Right? So it's a very good null test to show that the K-band isn't contaminated. Better yet, a way of saying the same thing is to measure the optical depth. So this is the optical depth as a function, and this is the likelihood. And what's shown in the black is the a sum, so KA-QB. What's shown in red is QB, and what's shown in the blue is KA. Right? So they are consistent. But if you take the difference, if you take difference between Ka and QB, this is what you end up with. Okay? Best fit, tau is 0. Right? You don't see any cosmic signal. That's a very nice confirmation. That's a very nice null test as well. And as a result, our tau measurement is now 5 sigma. Okay. And compared to the 3-year results, the 3 sigma, now we have much better measurement. Not only because we had more years of data, but also we have actually more data to co-add. We add Ka. Okay.
Same mask for Ka and Qb?
Exactly the same mask for Ka and Qb. Yes, that's right. What does that buy you? So this is one of the press releases results. So by taking the new tau measurements and convert that into the redshift of reionization, assuming an instantaneous reionization, just the universe went from 0 electron fraction to 100% electron fraction at certain redshift. Then it turns out that the Z reionization is 11 plus minus 1.4, 1 sigma. What about Z equals 6? Because quasar measurements, Gunn-Peterson test suggests that the universe completed the reionization at Z equals 6, or maybe 6.5, something like that, something in that region, right? So can we say universe started reionization at the same redshift and ended at the same redshift? But now WMAP results exclude the Z equals 6 reionization at 3.5 sigma. And the 3 sigma lower bound is Z equals 6.7. So at this point, we can safely say that the universe didn't have this instantaneous reionization, but had to be a prolonged episode of the reionization. You can do a more complicated thing by saying that, okay, universe first reionized at Z equals R, Z equals ZR, to some electron fraction given by Xe, then fully reionized at Z equals 7 to Xe to 1. Then try to constrain 2 parameters. First, when the reionization started, and to what level. And this is the contour. So there's a long degeneracy curve. You can say even, for example, universe reionized at Z equals 25 to Xe of 0.2. Then fully reionized at Z equals 7. The model fits the data. But you can't really tell right now. So WMAP data are good enough to measure optical depth now. Okay? So you have very good measurements. But if you want to disentangle, if you want to probe the cosmic reionization history, then you need better data, say WMAP 9-year data. So that will be one of the things that we can improve using WMAP 9-year data. Cosmic neutrino background. Okay? So we know there are neutrinos everywhere, right? Have we actually seen it in the cosmic neutrino background? So how do neutrinos actually affect CMB? If you totally ignore neutrinos, then you underestimate the radiation energy density by something like 70%. So if you do that, then it's going to change radiation to matter ratio. Therefore, that's going to change radiation matter equality epoch, Z equality. Okay? So if you underestimate the neutrino species, then Z equality would be earlier. Well, if you had more neutrino species, then Z equality would be later. But not only that, but also neutrinos have their own perturbations. They are relativistic neutrinos. We're talking about relativistic neutrinos because we were talking about decoupling epoch. And we know that their masses are less than that. Neutrino perturbations affect the metric perturbations through Einstein's equations. They have anisotropic pressure, anisotropic stress, so they will affect the photon baryon plasma in a funny way. And what do they do? So this is the, now I'm sure you can't see it, but here you have actually 2 lines, blue and red lines corresponding to different number of species. And this is the difference between the two. Now you can see it more clearly. And this is the no neutrino case, neutrino case minus, this is a neutrino case, I'm sorry, no neutrino minus neutrino, okay? No neutrino minus neutrino, okay? So I think I said it the opposite way. Oh, anyway, whatever. Let me tell you the physical effects. One thing the neutrino would do is a suppression of the photon baryon perturbations. So you see the suppression here. Now I tell you, this is the neutrino minus non-neutrino case. Okay, you see the suppression. Yeah. Okay. This effect can be mimicked by changing tilt, NS. You also have the multiplicative phase shifts. For example, you have here, this is a longer wavelength modulation, and then you get higher frequency modulation. This is not additive shift, it's a multiplicative shift. This corresponds to shifting Z quality. This effect can be mimicked by omega mod h squared. But what cannot be mimicked, and this is pointed out by Sergei Vajinsky in Eurosurgic back in 2004, is the additive phase shift caused by neutrino anisotropic stress. You see here, the delta L is actually the same here. This effect cannot be mimicked by any known physics as far as you have these adiabatic perturbations. Okay.
This is because of the collisionless nature of neutrino, right?
This is
Anisotropic part of
and also, they trace it back to a very interesting effect where neutrinos' free spinning velocity, which is the essential speed of light, is greater than the sound speed of the photon baryon fluid. So you can actually perturb sort of super sound horizon, and this is the effect. Now, adding them up, you actually see the effect at the level of delta chi squared of 8.2 from WMAP data alone. Okay. This seems to be robust about actually the assumption about the initial power spectrum. We still see this, for example, when NS depends on scales. Still less than 3 sigma, but the confidence level that we put up with is this is the evidence for the non-zero and effective greater than 99.5% level. Yeah.
Can this be mimicked if you had another relativistic degree of freedom which was not a neutrino? Let's say you had another photon which does not interact with us, but does interact with itself, so it only has isotropic stress. Would that look different?
Oh yeah, that would be identical. That would be identical to neutrinos.
There is no specific of neutrino.
No, it is a collisionless with itself. But
Yeah, so
with itself.
collision not. Oh no, I don't think so because this is coming from anisotropic stress.
Yeah, isotropic stress.
If they are collisional, they don't have anisotropic stress.
Exactly.
No high.
Yeah, that is not a lot.
And let me just show you what we are seeing is not the effect coming from Z equality. So this is the a contour plot of a number of relativistic species versus omega mod h squared. And you see this massive degeneracy, right? But what's shown in the line is a constant Z equality line. Constant Z equality predicts that any effective can be, happily zero if you reduce omega mod h squared to a very low level. And this is again showing you Z equality and the number of neutrino species, and constant Z equality will just tell you that you can arbitrarily get down to n effective equals 0. But data don't show that. So this is not coming from Z equality effect. This is coming from neutrino anisotropic stress effect. And if you add, say, I will tell you what the BA on SN mean later, but if you add other data sets like baryon acoustic oscillation, supernova, and HST, you can break degeneracy. And then you can have a better measurement of number of neutrino species, effective number of neutrino species, 4.4 plus minus 1.5. And you can now compare that to, so this is the measurement at the decoupling epoch, Z equals 1090. You can compare that to Big Bang nuclear synthesis, or you can compare that to even more precision measurement of the decay widths of Z bosons in lab. They are consistent. So that's pretty good. Z equals 10 to the 9, Z equals 1000, Z equals 0. It's pretty good confirmation of the standard picture. What about testing inflation?
That rules out the large relativistic backward and say gravity waves.
So can we, you're asking, for example, can we constrain omega gravitational wave in this way? Yeah. But I think the limit from this is probably more stringent. But yeah, sure. Yes, that's right. Oh, from this and that?
Yeah, the bound.
I see.
Identical to CMB at first constraints it down with even lower.
So despite the size of the error, they are actually.
So they did an estimate of so Planck they claim will get that back like factor 5 better than the current again.
I see.
But
Mm-hmm.
well, at least with 3-year data, so yeah,
I see.
they were comparable.
Good. Okay, testing inflation. So in the press release, we said we now have much better understanding, much better constraint on inflation. What do we mean by those? So we tested out like 5 predictions from inflation, universal flat, adiabatic perturbations, Gaussian, near scale invariant, and gravity wave. So let me just quickly walk you through all of this. But before you go into that, let me just remind you how CMB constrains inflation. So CMB to cosmological inflation, okay? So we measure peak locations. That will give you distance to the scalar surface. That's sensitive to geometry. So that will give you constraint on inflation through flatness, okay? Then you have overall tilt of the power spectrum. And that's sensitive to the initial perturbation power spectrum generated from inflation. So that will give you the shape of the primordial power spectrum. That will be giving you constraint on inflation. What about polarization? Large angular scale polarization, both E and B are sensitive to primordial gravitational waves. So that will give you gravitational wave constraint, and that will give you constraints on inflation. Or you also have this temperature polarization cross correlation, and that's sensitive to both gravitational waves and non-adiabatic perturbations. I will tell you a little bit more about that, and that will give you the constraint on inflation. So that's the kind of piece of information that we're using in the CMB to constrain inflation. So let me just tell you a little bit about tilting. Actually, it's better this way. This is a tilting, right? You tilt. If NS is less than 1, then you get more power on large scales, but less power on small scale. But if it's blue tilt, then you get less power on large scales, but more power on small scales, okay? All right. So what do we know about that? Now, tau, optical depth, has a very similar effect. If you had a more tau, it suppresses more small scale power. So it's fairly degenerate with NS. At least it used to be degenerate with NS, right? But not anymore. With 5-year measurement of tau, degeneracy is almost lifted. Not perfectly, but to the level that it's now subdominant. The dominant degeneracy is now coming from NS and omega baryon H squared. Okay. Omega baryon H squared also has a similar effect. If you had a larger omega baryon H squared, it damps photon baryon oscillations at small scale. So it's really similar effect, right? But now we're limited by omega baryon H squared, not tau. Therefore, as long as you are not improving omega baryon H squared, say baryon acoustic oscillation supernova, they have nothing to do with omega baryon H squared. You're not going to improve on NS. So you have to say measure the small scale CMB more accurately to do that. And now we have this NS measurement that's less than 1 at about 2.5 sigma from WMAP data alone.
So why do you say 2.5 sigmas when it intersects the 2 sigma contour?
Okay, so this is the one-dimensional marginalized constraint, right? This is the projection of that. But if you're willing to say, for example, I know that omega baryon H squared is actually 0.024. If somebody tells me that, then that will quickly give you NS equals 1, right? But if you just project this out to the one-dimensional plane, this is what you get. So that's 1.5 sigma. But you can take a look at that statement in a different way. When you have degeneracy, that's what happens. So now I think it's pretty actually important to get omega baryon H squared nailed down if you wanted to measure NS precisely. That's going to be challenging, though.
So when will be a big factor blessing?
Yeah, it's actually, you can fill in this entire plan. I looked at that, actually. I was curious about how good the BBN constraint right now. It's not good. All right, now WMAP data alone can do actually pretty well. You've just seen that. But we can improve a lot of parameter space by adding more information from, say, supernova baryon acoustic oscillations. Let me just say a little bit more about that. So, for example, the one example is flatness of the universe. So what's shown here is omega lambda and omega curvature, right? WMAP data alone, it's massive degeneracy, and you're happy with omega lambda equals 0, and positively curved up to 30%. You're happy, okay? You can fit the data. Why is that? Because WMAP measures angular diameter distance to single redshift, z equals 1,000. But that, of course, is sensitive to curvature, but also sensitive to omega matter. You can get exactly the same angular diameter distance that way. I mean, that's the geometric degeneracy that was pointed by Dick Bond and George Eftathiel. So you essentially need 2 angular diameter distances, right? You need z equals 1,000 and maybe z equals 3. If you had 2 distances, then you can break this degeneracy. Well, if you had, say, HST measurement, that's also distance scale. So you can break the degeneracy. So as soon as you say use HSD or supernova or say baryon acoustic oscillations, you can break the degeneracy and quickly, you conversion to here. Okay.
It's almost all from BAO, right? I mean, BAO alone.
Yeah, I'll get to that. Yes. Yeah, I'll get to that. So this is the type 1A supernova data. Well, that's what we use. Okay, and BAO. So this is the baryon acoustic oscillations as seen in the galaxy spectrum. So you've already seen baryon acoustic oscillations as seen in CMB, but this is the same thing as seen in galaxy. So you can use this to measure distances to z equals 0.2 and 0.35. So we have 3 data points, z equals 1,000, 0.35, and 0.2. Okay. What does that get you? You get this. Now, as you already pointed out, most of the information is coming from BAO, and why is that? BAO is an absolute distance indicator. Okay? That means when you have CMB and BAO at 2 different redshifts, you have 2 absolute distance measurements. But supernova are actually not sensitive to absolute distance. They are only sensitive to relative distances. So they are not as good in measuring the curvature as BAO because they are relative. So just having these 3 data points, adding BA and WMAP will get you very good measurements on omega k. Right? What does that mean? Oh, by the way, you can do this by using, by allowing for the non-zero, non-1 W. So even if dark energy is not -1, you can get a fairly tight constraint by using BA on supernova. Okay. What does that actually mean? So these are fun numbers quote. If you are teaching astronomy or cosmology course in your class, these are maybe the fun numbers quote actually. Omega k 0.017, right? Who cares about that? If you teach that in your class, your teaching evaluation will be horrible. But you can restate the same statement in terms of curvature radius of the universe, right? Because after all, omega k is defined by this formula, where our curvature is the curvature radius at the present universe. So because it's a square root, you get different answers depending upon sign of omega k. Let's take negatively curved case. Then you say curvature radius is greater than 33 h inverse gigaparsec. Pretty big. Compared to particle horizon, that's 10 h inverse gigaparsec, right? So we are not seeing the curvature radius within the observable universe to this level. So that's pretty good number to know. What about inflation? Details aside, you can look up that in my paper. Because the universe is flat, inflation should have lasted for a long period to make the universe sufficiently flat, right? So now we're not seeing any evidence for curvature. What does it imply for the duration, total duration of the inflation? It turns out that the logarithm, log of expansion factor turns out to be something like 36 or greater for reheating temperature of about 1 TeV. And factor of 10 improvement in omega k will shift this up by about 1.2. Factor of 100 improvements will push it to factor of 2. So that's not large factor, but nevertheless, this is the observational constraint on the total duration of inflation, right? Now, let's say but if curvature is measured, okay, this is the lower limit. If curvature is measured, then we quickly nail down the total duration of n, total duration of total E-force to this level. This is the kind of level that we are talking about, right? But at the same time, we have various reasons to believe that the n has to be something like 50 or 60. So combining these two, we can actually nail this reheating temperature. So that will be interesting to do.
60 is for high energy inflation.
Yeah. So you actually can break the degeneracy in determining reheating temperature. That will be interesting to see. Adiabaticity. Okay. So we have pretty good measurement of adiabaticity. So what does adiabaticity actually mean? It means radiation fluctuation, the matter fluctuations obey this relationship. Okay. Just remember this. And I wanted to just get one number out of this. I just wanted to get one number telling me how much deviation is allowed from this relation. Now, there's a very simple-minded way to do that. Let's say this is A, this is B. And I do A minus B divided by A plus B divided by 2. That's the simplest thing you can do, right? And because no one has done this, I just put the name, adiabaticity deviation parameter. It's an ugly name, but anyway. But if delta addi is 0.02, say, then we say radiation and matter have to obey the adiabatic relation to 2% level. It's a very simple number. Okay, now this is the 5-year temperature polarization power spectrum. You have oscillation. And adiabatic perturbations, super horizon scale fluctuations, will give you this negative TE correlation. It's a distinctive signature. It's almost a proof that you are dominated by adiabatic perturbations. And that's nicely illustrated in Spark and Zaldariaga 1997. Non-adiabatic perturbation, any deviation from adiabatic perturbation will essentially give you shift in this zero, and it's going to fill in trough, shift to the peak, and so on. So you can just use peak structure to constrain TE, to constrain non-adiabatic. We, of course, use the full data sets to do this, but that's the kind of information you can get from TE. Just details aside, most of the people like to use, say, entropy perturbation squared divided by curvature perturbation squared to quantify the deviation from adiabaticity. That's called alpha. So that's what we use. But you can translate that number into this simple-minded delta addi by this relation. Anyway, we use two scenarios. We haven't explored a whole lot scenarios. We just picked two representative, perhaps most interesting cases. First case is axion. So what if dark matter is axion? Right? Axion entropy perturbations are not correlated with adiabatic perturbation. So that's a simplification you can make. So let's see what you get. Or curvaton type, there's a so-called curvaton scenario. If you are not familiar with, don't bother. But distinctive signature of this curvaton scenario is that the entropy perturbation and the adiabatic perturbations are anti-correlated, or correlated depending upon the sign for the curvature perturbation that you take. Well, details aside, we're just looking at uncorrelated entropy perturbation or anti-correlated, okay? And let's see what we get. And this is also no evidence for entropy perturbation, no evidence for the deviation from adiabatic. If you think dark matter is axion, then your entropy perturbation has to be less than adiabatic by 9%, okay, or less. That's a number you can take away from this plot. Now, WMAP data alone gives you some constraint, but it's actually degenerated with NS. Non-adiabatic perturbation tends to give you more power on large scale. You can compensate it by tilt. But that tilt is also degenerated with omega matter h squared. Anything that's correlated with omega matter h squared can be broken, can be determined better by adding BA on the supernova, because these are measuring essentially omega matter h squared. So you quickly, you remove the resiliency and you get down to this level, about a factor of 2 improvement in the constraint, and you get this fairly impressive number, like 9%. If you are willing to say dark matter is curvaton, not axion, then constraint is even better. Deviation from adiabaticity has to be less than 2%. That's pretty impressive. Gaussianity? Yes.
Include, two of the company had a 20-parameter isotropy model where you could vary all possible phases between all the species, and you could imagine isotropy varying, and he concluded, and there is the power spectrum of each is a function of k, and he concluded that you could mimic anything you see. Is that true, or is that not true anymore?
I'm not sure. We haven't tried. Yeah.
That's a question. Yeah, maybe
Yeah.
Anyways,
Maybe.
Maybe. Function.
We haven't done that. All right, Gaussianity. So in the simplest model of inflation, prediction is that your fluctuation should be pretty close to Gaussian. Is that true? All right, so if you want to test Gaussianity, you can do the following thing. If you fluctuation of Gaussian, your 2-point correlation function specifies everything completely. So you don't have to go beyond 2-point correlation function. You don't bother to measure 3-point function. But it's non-Gaussian, then perhaps you should take a look at the 3-point function right? Big 3-point function on the sky. Then you just measure the amplitude of the triangle and see if you see anything different from 0. So far, there are 2 physically motivated triangle configurations that you look. Squeezed, like that, right? And equilateral, right? All the sides are same. So let's see what we have, what do we say about the amplitude of these triangles. And no detections. So this squeezed triangle is this, and equilateral triangle is this. So consistent with 0 is in 2 sigma. There's some slight preference for the positive value of FNL, but it's not, not significant. But what these numbers actually mean, these numbers actually imply that the primordial fluctuations are Gaussian to 0.1% level. If you do this a minus b plus, divided by a plus b divided by 2, you say actually that these numbers imply that it's a Gaussian to 0.1% level. This is very accurately Gaussian. We know the flatness to 1%. We know the adiabaticity to say 2 to 9%. We know the Gaussianity to 0.1%. Okay? This is pretty impressive. Scale invariance. So if we add a BAO and supernova, what NS do we get? We get something like 0.96 instead of 0.963 with similar error. It's 2.9 sigma away from NS equals 1, but improvement is just nothing. No improvement, okay, essentially. That's because BAO or supernova don't care anything about baryon, omega baryon H squared. That's all. You need something like omega baryon H squared to do this. Running index, so is NS scale dependent? Answer is no to this level. So, well, power law spectrum is good fit. Okay. Simplest inflation model like m squared phi squared will give you running that's level that's 10 times smaller than current error. If you get down to that level, you may expect to see something, but not now. So this is consistent with simple inflation picture. What about gravitational waves? I'm, I guess, running out of time, so let me just speed up a little bit even more. So how do WMAP measure gravitational waves? Okay, B mode, right? You've heard about this, B mode, B mode, B mode. It's not just B mode. B mode will give you, some smoking gun for R, but actually gravitational waves give you also E mode and TE correlation. So just say, how much R we get by just using polarization information L less than 20. Just try to get maximum out of that. R limit is 20, right? It's just essentially too large to be interesting. If you add a TE correlation, however, to L of 450, you get it down to R less than 2. So it's 10 times better. So at this point, the actual information is dominated by TE correlation, not even B. And if you add a temperature, you can get it down to 0.2. Okay? So it's currently most of the information is actually coming from temperature, okay, not B mode. Assuming power law form, and I'm even fixing NS. If I'm not fixing NS, then the WMAP alone results upper limit on R is 0.43. Okay, that's something like 30% improvement from the 3-year data. But if you add BAO, actually you get it down to R equals 0.2. Even more significant is that now we're excluding NS greater than, we're disfavoring NS greater than 1 at more than 2 sigma level. Okay? So it used to be that NS is less than 0 only when R is 0. That's no longer true. Now, with this constraint, NS greater than 1 is now disfavored, regardless of R. That's very significant. And you can, for example, constrain now inflation models, right? So let's look at, say, models that can produce large gravitational waves. Say, take chaotic inflation model, then lambda phi to the 4th. Poor guy, right? It's completely out. M squared phi squared, it's here, doing a good job, but they are, pushing outside of the 1 sigma contour.
So why can't you adjust n further?
Why can't?
Like why not n of 200 or something?
n equals to, oh, this is the n, the fluctuations generated. That's not the total number of n.
This is from the moment of the pivot point to end of inflation.
Yeah. This is the n WMAP. Essentially, this is the n that W measures. Right.
This is the moment during inflation where wavelength goes outside.
Yeah.
This is wavelength corresponding to the pivot point.
Yes.
So inflation ends. You cannot it can be only lower.
You cannot increase it. No.
There was an interesting paper by Eiichiro Makarista that if you had a single field m squared phi squared, then this is what you get. But if you had n, like m squared phi squared field, looks like axion, then you can actually change prediction for ns. If you do that, if you take Eiichiro Makarista prediction, then if this number of UFOs is 50, it's pushed outside of 95%. Right? That's pretty interesting. You begin to discriminate between even inflation m squared phi squared and pure m squared phi squared. Power law inflation, so just forget about monomial, just do power law. Then you get this constraint. And depending on, so power law inflation, exponential potential will give you this power law inflation. And instead of exponential expansion, you get power law expansion. So let's say power index is P, and P less than 60 is ruled out at more than 3 sigma. P less than 70 is disfavored at more than 2 sigma, and so forth. You can interpret this again in the language of multi-field inflation. Let's say instead of saying single field giving you P something like 120, that's the best you can do with this model, P equals 160. Instead of saying that, let's say I have one field, many fields, each field has something like P equals 1. How many fields do we need to satisfy constraint? It turns out that you need 120 fields. So if you are willing to take that picture, then WMAP tells you that you need 120 fields. Okay? Finally, hybrid inflation. Hybrid inflation has this parameter region that drives inflation by vacuum energy, okay? Not by the slowly rolling scalar field. That tends to predict ns greater than 1. And you see that parameter region is now disfavored, okay? Regardless of R. That's where significance comes in. So you can really ruling out large region in a parameter space and really nailing down the classical inflation models. And we can, of course, continue to do better with the future years of data. How about putting everything in, like ice curvature, or in this case, running, so scale dependence of ns and R and whatever, then you get much weaker constraint. Okay. So in that case, ns greater than 0 allowed, R is still as large as 0.6, and so forth, if you do that. Well, that's all I can say about that. So let's grade inflation. Well, so far so good, right? So far so good. So what are we doing here? Okay. Essentially, in this interpretation paper, I talked about all these inflation constraints, right? And so far, no surprising discovery. Essentially, simplest inflation continues to do good. I gave you very quantitative limits on these inflation models, but essentially in the interpretation paper, we tried very hard. We tried everything we could do in the time before the data release, of course. We didn't have infinite amount of time to find deviation from the simplest 6-parameter lambda CDN, and we failed to find any. It's like you're in the dark forest, right? Trying to look for, is there any deviation from lambda CDN, right? Just did it. Didn't find anything. This is a status report or journal on this quest to look for new physics in WMAP. We didn't find anything, but I'll just give you the numbers, okay? So that you don't have to repeat you don't have to repeat this. How about dark energy? So look at the dark energy constraints, and just to sort of make the analysis easier, we came up with just 3 numbers to test dark energy. Instead of using full information in WMAP, just using 3 numbers like redshift of decoupling, acoustic scale, that's the peak position information, and also so-called shift parameter that gives you the ratio of the Hubble horizon size at decoupling and angular diameter distance. Well, details aside, just using these 3 numbers, you can get constraints like this. what's in the bottom. This is omega k, and this is W. Right. And this is BAO plus WMAP, supernova plus WMAP, and combined. This is using only 3 numbers that I just gave you. Okay. WMAP distance priors. I didn't use full data sets. This is what you get using full data sets. Constraints are slightly better here because you're using full data sets, but you can get very close by just using partial information that I gave you. And this is just quick and easy way to test, for example, time-dependent W. Here I'm just using these 3 numbers. Combine that with BAO and supernova, and just got this contour. No Markov chain, okay? Just chi-squared analysis. Right? Then, okay, well, as a result of that, what we found was that W is consistent with -1 and no time evolution. And I give you the numbers, okay? All right. Parity violation. So, okay, we used the TE correlation, EE correlation, BB correlation, and TT correlation. But you can actually have 2 more, TB and EB. But these are thought to vanish in the parity-conserving universe. Okay? If you violate parity cosmologically, then you produce non-zero TB or non-zero EB. We know parity is violated in weak scale, weak interaction. Why not violating it in cosmological scale?
You mean in the electromagnetic sector?
Electromagnetic sector, yes. So let's say we have this parity violating interaction that couples to photons. Then it's going to rotate polarization angle. Okay? So let's see what we know about that. So this is the TB power spectrum. Unlike TE power spectrum, it's 0, right? It's 0. Nice to see that, because if it's non-zero, then either it's a signature of new physics or signature of new systematic error, WMAP. And we can constrain the polarization rotation angle, delta alpha, by using this. So let's say you have non-zero TE, right? Then what you observe is actually TE rotated by this factor. And TB, that's normally 0, but you can generate TB from TE by rotating polarization. This is the formula, and you can use this to constrain delta alpha. And it turns out that delta alpha is consistent with 0. Something like minus 2 degrees plus minus 2 degrees is the constraint. And this is the constraint on the rotation angle between decoupling epoch, z equals 1,000, to the present. It's enormous path lengths. Let's compare this to astrophysical measurements. Like you measure a quasar at z equals 2. And measure the polarization angle. How much can you get the polarization angle rotated? And the result is something like minus 1 degree plus minus 1.5 degree. They're comparable. Okay? They're comparable, but the path length for this measurement is like up to z equals 2. We're talking about path length up to z equals 1,000. So this is a rather stringent limit on the amount that you can allow to actually rotate, or amount of the parity violation you are allowed to have in the UR Lagrangian. Right. Neutrino mass, 0.6 eV. Okay? So just WMAP data alone, you can get some constraint, something like less than 1.5 eV or so. Right. Total neutrino mass, okay? Summing over all neutrino species. You can improve on that by simply adding BAO and supernova measurements. And by adding the BAO, you actually fix the Hubble constant. This Hubble constant information helps you enormously to actually break degeneracy between neutrino mass and Hubble constant. I don't have time to get into the detail. Please read the paper. But that's what's happening. So by doing so, you can reduce the error by more than a factor of 2. And now your constraint is something like 0.6 eV, less than 0.6 eV. That's independent, by the way, on the normalization of large-scale structure. There was some confusion about this number, whether you marginalize over bias of the galaxy power spectrum or fix it, or things like that. This amplitude of the power spectrum is very difficult to nail down. But that's the direction to go. We have to go in that direction. But so far, just using this information alone, we could get down to this level. And I think that's pretty good. You can do much better by using amplitude information. All right, so after all this mess, after all this quest in the dark forest, looking for deviation from lambda CDM, hoping that you become famous by finding something significant, nothing happened. Well, this is the table number 2 in Komatsu et al. This is the status report, Captain. Just take it, and just send somebody else to the other forest and look for deviation from lambda CDM. Lambda CDM is annoying. We don't know what the dark energy is, what the dark matter is, but it's a pretty good fit to the data. You can really work hard to find deviations. It's pretty difficult to find deviations. What about this annoying lambda CDM? So BA1 supernova actually helps you to reduce the error on these lambda CDM parameters. Anything related to omega matter h squared, okay, can be improved. For example, sigma 8 also depends on omega matter h squared. You can reduce the error by some significant amount by adding BA on the supernova, because you're nailing omega matter h squared. Also, anything related to h naught can be improved. You know omega matter h squared, but you don't know what the omega matter is. But by adding h information, you shrink the error by factor of 2. I'm almost there. And we have here again, list of lambda CDM parameters. Okay. Not much change from the third year, but errors are much smaller now. And I'll give you the cosmic pie chart, okay, that you should use in your cosmology class. That's this. We get some ridiculously small error for age of the universe. 13.73 plus minus 0.12 giga-year. Omega baryon, 4.6%. Dark matter to 23% within 1%. It's pretty remarkable. Vacuum energy is 72%. That's a revised cosmic pie chart, and this is the chart that I can show here. But because we have the evidence for this cosmic neutrino background, we can even go one step beyond and say, what was the pie chart at z equals 1090? This is the pie chart at decoupling epoch. And then you see photons are still important, right? It's not completely matter-dominated. So photons 15%. Neutrino is something like 70% of that, so that's 10%. And baryons, dark matter ratio doesn't change. So dark matter is 60% and atom 12%, no dark energy. Okay. So summary, annoying lambda CDM still fits. We did everything we could do in time to find deviations. We failed. But we have a number of significant improvements in the quantitative limits. For example, to me, most significant finding was that R is now less than 0.2. In ns greater than 1 is disfavored, regardless of the R. I think that's pretty significant. And we improved on the determination of lambda CDM as well. And outlook. This is the last slide. So with more WMAP observations, what surprises do we expect to see? Non-Gaussianity, for example. We know the Gaussianity to 0.1% level. At that level, actually, you have some reason to expect some surprises. There are lots of theories out there that will give you something like that. Let's take the best fit value today, 50, right? And what can we do with 9 years of data? Well, probably if that's 50, we'll see it at about 3 sigma level with 9 years of data. That will be nice finding if that's the case. This is something we can test with 9 years of data. This R and S phase space will keep improving. And I think we can push m squared and phi squared out of the contour by 9 years, if this model is not correct. If it is correct, I think we have the evidence. We're going to have the evidence. But if not, it's going to be pushed outside of contours. Okay? And I think currently n greater than 1 is disfavored at more than 2 sigma, but I think we can convincingly rule out ns greater than 1 by 9 years. This is the sort of things we expect. Probably there are lots of other things, but this is the things that representative cases that we can make to extend WMAP mission to 9 years. I stop here. Thank you very much. Yeah. So for example, I didn't have a slide, but in a paper, for example, it's okay. What does the weak lensing buy you? If fixing the matter amplitude today, right? We measure matter amplitude at z equals 1,000. So anything that changes this relative normalization will be improved by including weak lensing. So what we could do, we did was to predict the sigmoid value as a function of, say, W, and as a function of neutrino mass, right? Then predict what the sigmoid is today. Error, so predicted error on sigma 8 is about comparable to this latest CFH legacy survey by Fu et al. The error on sigma 8 is something like 0.04, comparable. So I think they begin to add the information. But I think a future data set will definitely improve on that. But so far, it's still comparable. Yeah.
Looking at that, what about Lyman alpha?
Yeah, I have looked at that too. So for example, running, right? That's the actual only thing I looked at. The neutrino mass, when I tried to neutrino mass, my code crashed, so I couldn't do that in time. But anyway, running is this. And you can improve on the constraint by something like a factor of 2 by adding Lyman alpha. That's pretty significant, yeah. And still consistent with error. Yeah, just error gets tightened. Yeah. Yes?
Just a question on the curvatum. So what are the constraints on the curvatum model coming from adiabaticity? What does it translate into non-Gaussianity?
Okay, so the prediction for non-Gaussianity from this curvatum scenario, given the adiabaticity constraint, is that the FNL is minus 1.2. Yeah. Curvatum model. Yeah. So if we see some evidence for the positive FNL, it's gone. Yeah. Yeah. Yes.
So you mentioned that the M-square classical model will be pushing out if non-zero state is available. M-square classical model is not favored because you have n-run, non-zero n-run characterized.
Non-zero running?
Yes, running one sigma level. This is due to the suppression of low L multiples, L equals 2 and 3, which is dominated by cosmic invariance. You cannot improve in 9 years.
But the m-squared phi squared model does not predict running. And predict running at the level of 0.8 times 10 to the minus 4, or 0.88 times 10 to the minus 3.
Why the data is not favoring m-square phi square?
But-
Because m-square phi square doesn't favor running, so you favor the running.
But then you are not testing m squared phi squared. If you wanted to test m squared phi squared, right, what you can do is to just, take running that it predicts.
Why the data doesn't fit the m-square phi square? Because you have running.
No. I'm sorry. I think I confused you. Why m squared phi squared are disfavored? Because of this R and NS plane. And here, I'm assuming that the running is 0.
Do you use running in this?
No. I'm not using running here. This is assuming running is 0. So only NS and R. Yeah. No, it's 0.02. But in fact, if running is 0, it doesn't matter, right? NS is constant in K. It's a purely power spectrum. Because of.
It's reading, Martin is reading square phi squared because of R.
Right. It's 1.4.
It's a combination, right? Both R and then, yeah. That's right, yeah. So, okay, now, if we really wanted to rule out m squared phi squared, this is not the best thing you can do. You can actually take prediction and fix the parameter and fit the data, get the best fit chi-square. Compare that to the best fit that you get. But we don't have, right, where does that come from? That's not what we see. We don't see any evidence for running anyway.
So we can continue.
Yeah, right.